Alright, in this video we're going to use mesh analysis to solve some example circuits. So given the circuit shown on the slide, let's employ mesh analysis to find the circuit currents and voltages. So first thing we need to do is identify the meshes. So in this case we've got three, mesh A, B, and C. So we will define arbitrary direction mesh currents in each of these meshes. So I just generally draw them clockwise. I'll call them A, IB, and IC. Also note that this 5 amp source, I'm going to highlight it red, constrains the relationship between mesh current IB and IC. Remember in the last video, when describing any branch current, that branch current is comprised of the portion due to each adjacent mesh, in this case B and C. So we can write an expression for the 5 amp source that is comprised of meshes B and C. Note that IC is going the same direction as the 5 amp source. So 5 amps is going to be equal to IC, and IB is in the opposite direction, minus IB. So this is going to be defined as a constraint. It's really defining the relationship between meshes. Okay, so now we're going to write KVL equations at each mesh. So first at mesh A. Traverse across the 10 ohm resistor, that's a voltage drop. We're going clockwise again like in the last example, so I'm going to call the voltage drops negative signs. It's a negative 10 times the current through the 10 ohm resistor. It's only current, mesh current IA. Then the drop across the 2 ohm resistor, it's going to be IA. There's two currents going through that one. IA and IC is in the opposite direction, IA minus IC. And then the 3 ohm resistor will be IA minus IB. I'm going to mention again, the reason I like to use this convention is I can look at this equation and interpret the equation directly without looking back at the chart. I see these negative signs out in front of all my passives, denoting that they're voltage drops. The first term in my current expression is always the current that I'm working with from the mesh that I'm working from, so in this case mesh A, and then the one I subtract off is always the adjacent mesh. So IA minus nothing because it's not adjoining any other meshes, IA minus IC because A is joined up with C through the 2 ohm resistor, IA minus IB because A is joined up with B through the 3 ohm resistor. Okay, moving on to mesh B. First, we're going to traverse across the 100 volt source. That's negative to positive, so that's a plus 100 volt term. Then through the 3 ohm resistor, that'll be times IB minus IA. Again, we're working from B. Adjacent is A. And then we get to the point where we see this 5 amp source. Okay. I find that this is a common area for mistakes. Don't assume that that potential is 0. This current source can maintain that current 5 amps regardless of the voltage across it. Since we don't know what it is, we just need to define something. I'm just going to arbitrarily pick that is going to be value Vx, positive on the top, negative on the bottom. Again, it doesn't matter if you choose positive on the bottom, just go by your convention that we used to set up the sign of each element in these KVLs. So as we traverse through this, we go from positive to negative. That's a voltage drop. So I'm going to subtract off voltage Vx, which is across that 5 amp source in my KVL. And then I get to the 6 ohm resistor and I get minus 6 ohms times current IB to get the voltage drop across the 6 ohm resistor, excuse me. And finally at mesh C, again, I'll start in the bottom left corner. The first thing I do is go across this 5 amp source, negative to positive, so that's going to be plus Vx volts. Then minus 2 ohms times the current through the 2 ohm, which is IC minus IA. Then across the 50 volt source, positive to negative. So that's a voltage drop of 50 volts. And then the voltage drop across the 4 ohm resistor is given as 4 ohms times IC, that equals 0. Okay, so let's look at the system that we've built. We've got 3 unknown currents, IA, IB, and IC, and unknown voltage Vx. Okay, so that's 4 unknowns, 3 KVL expressions, but remember the constraint expression that we defined at the beginning relating IC and IB together. In other words, unknowns IC and IB are not independent. They are related to one another, and that's because of this 5 amp source. Therefore, the 4 equations can be solved, getting us the 4 unknowns. And our solution is IA equals 1.25 amps, IB equals 1.75 amps, and IC is 6.75 amps. Note from these mesh currents we can find any other parameter that we want in the circuit. For example, let's say we want to find the power absorbed by the 2 ohm resistor. Well, we need the current through the 2 ohm resistor. And the current through the 2 ohm resistor, which we could just arbitrarily define as I2 going from right to left, is comprised of currents IA and IC. Okay, so we know that the power of the 2 ohm resistor is given as the voltage across the 2 ohm resistor times I2. Note that since we wrote I2 going from right to left, I'm implying that V2 is negative positive from left to right. Okay, so I2, we can rewrite this expression as all we really need is V or I, right? So if subbing in Ohm's law for V, I get I2 times 2 ohms times I2, which equals I2 squared times 2 ohms, where I2 is given as the summation of IA and IC, where IC is in the opposite direction, so IA minus IC, quantity squared times 2 ohms. Again, this is just relating branch current I2 to mesh currents IA and IC in the same way we use to construct our KVLs. So you can do this method for any element in this circuit to find the specific powers. The point is, once we find these mesh currents, any other parameter in the circuit can be determined. Okay, let's solve this problem one more time. So I'm looking at exactly the same example, and remember that we found right away that the mesh currents IC and IB are related to each other because of this 5 amp source. So this constraint is what has a special name, and it's what we call a supermesh. And that is that mesh B and mesh C are not independent of one another. So it turns out that we can group these two meshes together into this supermesh because of this 5 amp source that relates the two together. Okay, and only write a single KVL of the supermesh. What this amounts to is that voltage Vx across the 5 amp source that we solved for last time doesn't have to be solved for if we don't want to. If you need the power of this element, of course you've got to solve for Vx. But if you don't solve for it. So in this case, for solving this as a supermesh, we still need KVL of mesh A, at which point it's going to be negative 10 ohms times IA. I'm going to go quickly through this because we did it last time. Minus 2 ohms times IA minus IC, minus 3 ohms times IA minus IB. Okay, and then what we can do is do a KVL of supermesh BC instead of a single individual KVLs. And so in this case, again, I'll start at the bottom left corner here. First thing we do is traverse across the 100 volt source, so that's plus 100 volts. Across the 3 ohm resistors, minus 3 ohms times current IB minus IA. Then we're going to skip over to mesh C, go through the 2 ohm resistor. That's going to be with current C, so IC minus IA. Then dropped across the 50 volt source through the 4 ohm resistor times current IC, the 6 ohm resistor times current IB, and we're done. So note that this expression is a little bit longer because we have more terms, but what this amounts to, if we go back to the last slide, we're taking KVL mesh B and subbing it into the KVL expression for mesh C, and that's basically taking the voltage across the 5 amp source and subbing them into each other, or setting them equal to each other, whichever way you want to look at it, and you end up with this exact same expression. So in looking at this now, we have unknowns IA, IB, and IC, 3 unknowns, and we have 3 expressions. 2 of them are KVLs, A and KVL BC, and the third expression is defining our supermesh constraint between B and C. And again, the system can be solved, 3 equations, 3 unknowns, and we get the identical solution on the previous slide.